Hello and welcome to this next session on instrumental analytical chemistry, where we will be talking about the second part of Redox Titrations 2. We'll be talking about some of the things that we need to do before we're able to do a redox titration. We'll talk through some of the indicators that might exist. We'll talk about some of the pre-processing techniques such as pre-oxidation that is required. We'll also talk about some of the indicators in more depth, such as the starch indicator, starch iodine indicator system. Okay, so let's get started with redox titrations part 2. So last time we talked about redox titrations, and we saw that they had properties which were not totally dissimilar to those properties observed in things like acid-base titrations. This was in the sense that they had both the reactions which were occurring. In the case of an acid-base titration, you had an acid such reacting with a base, so the proton reacting with the hydroxide in like a Bronsted-Lowry or an Arrhenius type reaction, and then that would produce a salt plus water. In the case of redox titrations, we also have a reaction occurring. This time, though, it's an oxidation reduction reaction between an analyte and a titrant. So one species is oxidizing the other, and one species is reducing the other. So we had this; these are analogous to acid-base titrations with equivalence and endpoints. So here we can see the kind of titration curve that we might see for redox titration, which is not totally dissimilar in shape to the kind of curve that we might see for a typical acid-base titration. So we have here, instead of a change in pH, we have a change in potential. This is the voltage, the potential, which is measured at the working electrode versus the standard calomel electrode in this case. Of course, though, you could use any kind of electrode, reference electrode that you desire. And then we have equivalence values here. The equivalence point is, of course, whenever all of the analyte has reacted with the titrant and there is no more analyte remaining. And after that, we will just be getting the response from excess titrant. So finding the endpoints, this is an important thing to do. So much like acid-base titrations, we can also use colored indicators. So a redox indicator changes color when going from its oxidized to its reduced state. So an example of this would be for iron. We have oxidized ferroin here, which is iron 3+. And when it is complexed with this ligand here, which has got a conjugated system, which, as we may recall from UV vis spectroscopy, will most likely have some intrinsic color associated with it. Now, this is true, and it has a pale blue color whenever it is in the oxidized state. This is iron 3+. But if we were to reduce iron 3+ to iron 2+, we would see that there would be a change of color, and we would now have a red color for our solution because of the presence of this reduced complex. So the color changes will occur over the range where the potential is equal to the standard potential plus or minus this 0.05916 over N reaction. And so that is 1 in this case. So it would be the standard potential plus or minus 0.05916 volts in this instance. A redox indicator will give a satisfactory endpoint when the difference in the formal potential is going to be less than 0.4, greater than 0.4 volts. So the redox indicators are listed here. So these are some of the common indicators that we can have. We have things like phenylsafranine, indigo tetrasulfonate, methylene blue, diphenylamine, 4'-methoxy-2,4-diaminoazobenzene, diphenylamine sulfonic acid, diphenylbenzidine sulfonic acid, tris-2,2' iron, tris-110 phenanthroline iron, which is the one we just saw, the ferroin. Then we have some tris-5-nitro-110 phenanthroline iron, and we have tris-2,2' ruthenium. So these are some common redox indicators. So whenever they go from the oxidized form to the reduced form, we have a color change typically. Some are going from color to colorless, and some are going from a light color to a much more vibrant color. And we can see the standard potential, reduction potential for these different indicators. So how do we find the endpoint? Well, typically we have to use something called a grand plot. A grand plot uses data from well before the equivalence point to locate the equivalence point. Now, why is this? Well, see, the problem is at the equivalence point, there's a very rapid change in potential. That's the rather steep part in the curve that we saw earlier. And this makes it difficult to accurately assess where the equivalence point is going to be. And so it's better to use the part before that almost vertical part in the potential change to try and estimate where the endpoint would be. And so we do that by measuring the potential at various points before the equivalence point and using that and extrapolating or interpolating to the data that we want to obtain. So data from close to the equivalence volume are not accurate because electrodes are slow to equilibrate when one member of the redox couple is nearly gone. Because it's kind of due to the activity. So if the concentration is low, then there's not going to be as many ions around to interact with, to oxidize, or to reduce, depending on what kind of redox titration we're doing. And so that kind of slows down the process. And so it takes a long time to equilibrate. And so it just sort of slows down the process. So it's easier to do it whenever there's still an abundance of both the analyte and the titrant. So a graph of the potential times 10 to the minus NE over 0.095916. So this is the inverse of the Nernst equation versus the potential, or versus the volume added, should be a straight line with x-intercept equal to the equivalence volume. So it's the volume times the inverse of the Nernst equation versus the volume. So there's the volume, there is the inverse of the Nernst equation. They've multiplied this by 10 to the 10 in order to make it easier to read just for our human eyes. That's not actually part of the equation, this part. This is the part that we calculate, but by multiplying it by this, we get a number which is easier for our human eyes to read, because you can see here, this is all 10 to the minus 11, 10 to the minus 10, and so on. So finding the endpoint then. So many analytical procedures are based on redox titrations of iodine. Iodine forms a very nice colored blue, deep colored blue solution whenever we add a little bit of starch due to a starch iodine complex being formed. So the iodine here is inside of the starch. So starch is the indicator of choice because the starch iodine complex is an intense blue color. So that's due to the interactions between iodine and the different polysaccharides within the starch. And so that forms these cages which hold and coordinate the iodine in the center. And that creates this kind of like conjugated system, which produces this incredibly vibrant dark blue color. And it's really, really obvious initially. Like once you add a little bit of starch to a little bit of iodine, you just get this super duper dark blue color. It's almost black. It's so blue. So sometimes we need to change the oxidation state of the analyte in order to make our redox titrations a little bit easier to do. So what we do is some pre-oxidation, where powerful oxidants that can easily be removed after pre-oxidation are used. So peroxide sulfate with silver plus as a catalyst results in this conversion to sulfate. So excess reagent is removed by boiling the solution after oxidation of the analyte. So that's the pre-oxidation with peroxide disulfate and silver plus. So you can see here there's an oxidation reaction going on. So silver 2 oxide, so here is a silver oxide, dissolves in acids to give silver 2 plus, which can be removed by boiling. Adjustment of the analyte oxidation state can also be done with solid sodium bismuthate. So here we have sodium bismuthate. So sodium, this is bismuthate anion. So this is a -1 complex anion. So the bismuth is in the +5 oxidation state because oxide is typically -2. -2 times 3 is -6. But this overall is -1 because this is +1, meaning that we have a bismuth in the +5 oxidation state. So the sodium ion is +1, Bismuth is +5, and then the 3 oxygens together are -6, which gives us our neutral complex. And so any excess solid remaining after this is removed by filtration. So that's a pretty easy process to do. Hydrogen peroxide then is a good oxidant as well in basic solution, and it can reduce chromium or dichromate to chromium 3+ and permanganate to manganese 2+. It spontaneously disproportionates in boiling water. So we have here the peroxide, which in boiling water, even actually just like in relatively warm water, it's going to decompose to give oxygen and water. It's called disproportionation because what's happening here is both an oxidation and a reduction. So if we look at the oxidation states of the various ions here, we can see that they will, so here we have a +1 oxidation state for our hydrogen, and we have -1 for our oxidation state of our oxygens, in the individual oxygens. So it's +2 and -2. So over here, we have an oxidation state of 0 for the oxygen. And here for the hydrogens, we have +1 still, and we have -2 for the oxygen, or the oxide in this instance. So the hydrogen is stayed the same, so nothing's happened there, but the oxygen has been reduced, i.e. it has gained an electron to form the -2 in the water, and it has been oxidized to form the neutral oxygen in O2. So it is the hydrogen peroxide is disproportionated and done both things. So a disproportionation reaction is one in which a reactant oxidizes and reduces itself. Pre-reduction then, so this is much like the pre-oxidation that we just did, but in this case, we're not adding electrons. So stannous chloride, this SnCl2, reduces iron 3+ to iron 2+ in hot hydrochloric acid. Excess reductant is destroyed by adding mercury dichloride. So the stannous chloride, the Sn2+, plus the mercury chloride gives us tin 4+, sorry, and dimercury dichloride plus 2 chloride ions. And so we see here that the tin 2+ has been oxidized to tin 4+, and the mercury has been here has been reduced from +2 to -1, or to +1, sorry. Chromous chloride, sometimes used to pre-reduce analyte to a lower oxidation state. Excess chromium 2+ is oxidized by atmospheric oxygen. Sulfur dioxide and hydrogen sulfide are mild reducing agents expelled by boiling an acidic solution. So we acidify the solution a little bit and then boil it, and you'll get sulfur dioxide, which smells like rotten eggs, and hydrogen sulfide, which smells relatively similar. So do it in the fume hood, do it under containment, or else the people around you in the lab may not be very happy. I mean, it's not going to be super bad for your health, but it's just not going to smell very good. An important pre-reduction technique uses a packed column with a solid reducing agent. So this is basically pre-prepared in, well, you can pre-prepare it, or you can just prepare it for single use. Is a burette basically filled with a solid reductant. So it's a little bit like column chromatography, which we haven't talked about in this class, but you may have come across before. In this case, we pack the column with this sort of setup here, which looks similar to a burette, but because of the sintered glass disc, it's not called a column. This column is packed with a solid reductant. So what happens is that the analyte solution filters through this over time, and as it interacts with the solid reductant, as it passes through, what happens is that it is reduced, the analyte is reduced, so it is gaining electrons. Then it passes through the sintered glass disc, and it does that so that the solid reductant doesn't clog up the burette down here, and then we get the reduced analyte down at the bottom. So a Jones reductor is a column packed with zinc, coated with zinc amalgam. It's not very selective. It basically just reduces everything. A sort of a more selective version of that is called the Walden reductor, which is a similar column. So both of them kind of look like this, but it's filled with solid silver and a 1 molar hydrochloric acid solution. And this is more selective than a Jones reductor is. Okay, so potassium permanganate is a common stoichiometric oxidation agent. So potassium permanganate, this KMnO4, is a strong oxidant with an intense violet color. It is reduced to manganese 2 plus in strongly acidic solutions, where we have the manganese or the permanganate here reacting with protons and electrons to be reduced to give manganese 2 plus plus some water. And this is the standard reduction potential for that transformation. In neutral or basic solutions, solid brown or manganese oxide is the product. So permanganate plus protons gives is reduced using some electrons to give manganese oxide plus some water, giving with a standard reduction potential here. So there are fewer electrons available, there's fewer protons. So what's happening here is the oxidation state is going to be different. It's not going to be the same as this one. Because in neutral or basic solutions, there just isn't the same availability of the proton and the electron. In strongly alkaline solutions, green manganate ion is produced. So this is whenever there are not very many protons available at all. And that makes sense in strongly alkaline solutions. So that's strongly basic solutions where the concentration of hydroxide dominates and there's very, very small concentration of protons. So what happens is we get the green manganate ion produced where the oxidation state is still reduced, but the oxidation state is much higher than it would be in the other two here. Potassium permanganate, which is not a primary standard, is standardized by titration of sodium oxalate. So how do we make a standard out of our potassium permanganate? We standardize it by titrating it with sodium oxalate. So here are some analytical applications of permanganate titrations. So we can analyze various different species. So we have here iron 2 plus. So that gives us the iron 2 plus is the oxidation reaction. So we oxidize iron 2 plus to iron 3 plus plus an electron. So here iron 3 plus is reduced to iron 2 plus with tin 2 plus or a Jones reductor. Titration is carried out in a 1 molar sulfuric acid or 1 molar hydrochloric acid solution containing manganese 2 plus, phosphoric acid, and sulfuric acid. Manganese 2 plus inhibits oxidation of chloride by manganese oxide, phosphoric acid complexes iron 3 plus to prevent formation of yellow iron 3 chloride complexes. Here is the reaction with oxalic acid. So this is the standardization with sodium oxalate, but this is oxalic acid. So it can oxidize oxalic acid to give CO2, some protons, and some electrons. We can also react with bromide, with hydrogen peroxide, nitrous acid, arsenic 3 plus, tin 3 plus, molybdenum 3 plus, tungsten 3 plus, erbium 3 plus, titanium 3 plus, and various other ions here, generally forming, generally needing to be standardized with oxalate in this case, so that we form the complex. Then we have some phosphate, and we have some tetrasulfuric acid. So oxidation with cerium 4 plus. So cerium 4. So we already saw this yesterday or last time with the cerium 4 plus titration of iron 2 plus. So what happened there was the iron 2 plus was oxidized to form iron 3 plus, and the cerium was reduced to form cerium 3 plus. So we already know that cerium is a good oxidation agent. It's useful in redox titrations. So cerium 4 binds anions such as perchlorate, sulfate, nitrate, and chloride. Variations of the cerium 4 plus, cerium 3 plus formal potential is indicative of these interactions. So cerium 4 plus plus an electron is in equilibrium with cerium 3 plus, and we have formal potentials here with different potentials for the different acids that it may or may not be in. So in these instances, in the various different solutions, like the higher this formal reduction potential, means the higher the probability it will be to gain an electron. So in the perchloric acid, this cerium is more likely to gain an electron than it is in sulfuric acid, which means that it's going to be a better oxidizing agent in perchloric acid than it is in sulfuric acid. So cerium 4 plus is yellow and cerium 3 plus is colorless, but the color change is not distinct. So that means that we can't really use that color change as an indicator. I mean, yellow versus colorless, especially in a dilute solution, is kind of going to be really hard to tell the variation there and tell whether or not it's actually changed color or not. It could be complicated by the presence of other ions in the or other light, stray light coming from other places in the room or anything like that. Even the color of the light could affect it. Ferrowin, which we saw earlier, which was the 110 phenanthroline, and other phenanthroline redox indicators are well suited to titrations with cerium 4 plus. That's because they're pretty good at complexing those as complexing ligands. Cerium 4 plus can be used in place of potassium permanganate in many different procedures. So if you don't have potassium permanganate, but you do have cerium 4 plus, you can use that. Oxidation with potassium dichromate. Orange dichromate ion is a powerful oxidant that is reduced to chromic ion in acidic solutions. So the potassium dichromate here plus 14 hydrogens gives plus 6 electrons is a reduction to give the chromium 3 plus some water, and it has this standard reduction potential here of about 1.36 volts. So a pretty good reducing agent, or pretty good at gaining electrons, so pretty easily reduced. Dichromate is a less powerful oxidizing agent than permanganate and cerium 4 plus in acidic solutions. So if you need like a mild or a milder oxidation agent than those, then this is a good choice. In basic solution, dichromate is converted into yellow chromate ion, whose oxidizing power is nil. So we have here the chromate ion here plus water plus 3 electrons gives some chromium. The hydrated chromium, which has got a chromium hydroxide, chromic hydroxide, so plus 5 hydroxide ions, and this has a reduction potential of minus 0.12 volts. So the reason why this is the reason why the oxidizing power is nil, because if this is a negative value, that means it doesn't want to receive an electron. Remember, these are standard reduction potentials. These are the gaining of electrons. So if this value is negative, that means it's not going to take any electrons. It means it does not want those electrons. And so that means that it's not going to be an oxidizing agent in basic solutions. So potassium dichromate only works as a oxidizing agent in acidic or neutral solutions. If it's a basic solution, we get the conversion of the dichromate into the chromate ion. The chromate ion is not good at oxidizing. Potassium dichromate is a primary standard. It's been known for a very, very long time. It's a very, very useful way to oxidize something. It's milder than the permanganate or the cerium 4 plus. Solutions of potassium dichromate are stable and cheap, so you'll often find these in teaching labs or just in general chemistry warehouses or general chemistry storerooms, stockrooms. Indicators such as diphenylamine sulfonic acid and diphenylbenzidine sulfonic acid are used to find a dichromate endpoint. So we encountered some of those earlier when we talked about the redox titration indicators. So reactions can also be monitored with platinum and calomel electrodes. So platinum would be the working electrode. Calomel, of course, would be the saturated calomel electrode, which is our reference electrode. It's what minus 0.241 volts as its potential. Again, we said that potassium dichromate is not as strong an oxidant as potassium permanganate or cerium 4 plus, used for the determination of iron 2 plus. So what happens here is that the indicator, the diphenyl benzidine sulfonate, is going to be in its reduced form. It's colorless, but if we oxidize it, then we're going to see a change in color. So we go from colorless to violet. The violet color is quite strong. And so we see this oxidized version, which happens whenever we reach the endpoint, because at the endpoint, remember, there will be no more iron 2 plus to be oxidized. And so we'll end up immediately using this to oxidize the indicator, which will cause this to change color. So this is our diphenylbenzidine sulfonate. It has been oxidized, so it has lost electrons. So the electrons are given out. Okay, so methods involving iodine. So these are very important methods. They're used quite broadly. They're relatively cheap, and they're very easy to observe. So when a reducing analyte is titrated with iodine to give I2, the method is called iodometry. So if it's reduced, if a reducing analyte is titrated with iodine, an oxidant, it's called iodometry. In iodometry, an oxidizing analyte is added to excess I2 to produce iodine, which is then titrated with standard thiosulfate solution. So in a reducing analyte, it's iodometry. In an oxidizing analyte, it's iodometry. So different, like similar but different terms. For an oxidizing analyte, we cannot directly measure it using iodine. So what we do is we oxidize it. We use it to oxidize the iodine to produce, or the I2 to produce iodine, which is then titrated with standard thiosulfate solution. So we titrate this produced iodine with standard thiosulfate solution. So solubility of molecular iodine in water is enhanced by complexation with iodide. So iodine here can be complexed with iodide to produce I3 minus, where the equilibrium constant for that is heavily to the right-hand side, so it mostly forms the products. So this is the kind of reaction which is occurring within the system. So we have the iodine, which has been produced from the iodide, which was added to the oxidizing analyte in the iodometry. So in the iodometry, iodide is added to the oxidizing analyte. The iodide then is going to be converted into iodine. Then the iodine reacts with the excess, the iodine that's produced by the oxidizing analyte in iodometry is then converted into triiodide here, which whenever it reacts with the leftover iodine in the solution, forming this triiodide here, which then is titrated with the standard thiosulfate solution. Okay, which is then analyzed or detected using a starch indicator. So starch is used as an indicator for iodine. That's because of its bright blue color. In iodometry, this is titration with triiodide. Starch is added at the beginning of the titration, and the first drop of excess triiodide, after the equivalence point causes the solution to turn dark blue. And it is a very, very vibrant dark blue color. In iodometry, which is titration of triiodide, so this is where we're titrating with the standard thiosulfate solution, starch should not be added until right before the equivalence point. So the reason for this is because the starch triiodide complex is very strong, and it would outcompete the thiosulfate. So what would happen is if we added the starch initially, we would get an erroneous measurement, because what would happen is that the starch and the iodine would create a complex, and this would reduce the amount of iodine in solution. And then from our thiosulfate titration, we would only be titrating with the free triiodide, resulting in a lower value for the concentration of triiodide or iodine than we would have gotten otherwise. And so it's important to just add it around about the equivalence point. Because like I said, the complex that's formed there is very strong, and we'd end up with this very, very intense blue color, which wouldn't really be very helpful at that point. So the starch iodine complexes are temperature dependent, so you can change the temperature, and you can break the complexation, because this is the one that encourages the formation of the what do we call it? Encourages the formation of the complex. So preparation and standardization of triiodide solutions. So triiodide is prepared by dissolving solid I2 in excess potassium iodide. So it's that equilibrium reaction we saw before, where iodine reacts with the iodide in an equilibrium to form triiodide ions. The blind I2, so that's solid to gas and transferred to a different place within the same apparatus, is pure enough to be a primary standard, but it evaporates while it is being weighed. So that means that we need to do something different. So instead, the approximate amount is rapidly weighed, and the solution of triiodide is standardized with a pure sample of analyte or sodium thiosulfate. So we can titrate it basically to find out the actual concentration, because the triiodide solution in water is pretty stable. However, if we acidify it, it's going to be unstable, because the protons will interact and react with the triiodide. And standard triiodide can be prepared by the reverse disproportionation reaction, where we have iodate plus iodine plus 6 protons gives us triiodide plus water. So that's a standard I3. It's a reverse disproportionation reaction, because the same iodine is being both oxidized and reduced to form triiodide. Here, the triiodide is in like a complex oxidation state, where there are 3 of them, 3 iodines atoms, and they oxidation state here. Whereas here, this is a -1 oxidation state, -1 to, well, -1/3. It is an oxidation. And then this one here is going to be reduced from the iodate, where it's actually in a positive oxidation state. It's going to gain electrons, it's going to be reduced. So this one is oxidized, this one is reduced, and then we get the formation of the triiodide. Use of sodium thiosulfate. So sodium thiosulfate is the universal titrant for triiodide. This is how we standardize solutions of triiodide. This is the reaction which occurs in neutral or acidic solution. So the triiodide oxidizes thiosulfate to tetrathionate. So you can see here this complex anion, and this forms 3 iodine molecules. This is also an equilibrium. In basic solution, triiodide disproportionates to iodine and periodic acid, which can oxidize the thiosulfate and sulfate anions. A stable solution of sodium thiosulfate can be prepared by dissolving the reagent in high quality, freshly boiled water. So dissolved carbon dioxide makes the solution acidic and promotes the disproportionation of the thiosulfate. So the thiosulfate plus an acid gives hydrogen sulfide plus sulfur solids. This might, if it precipitates out, would form a solid, a yellowish solid. Metal ions catalyze the atmospheric oxidation of thiosulfate, so that means the presence of oxygen. So 2 copper 2 plus the thiosulfate gives copper 1 plus the thionate anion. Then the can also happen here is that the copper 2 plus reacts with oxygen and protons to form copper 2 plus water. Analytical applications of iodine. So reducing agents can be titrated directly with standard triiodide in the presence of starch. An example here is the iodometric determination of vitamin C. So we have vitamin C here, which can be determined using our triiodide by forming the dehydroascorbic acid. So this is a common way of determining vitamin C in like various systems. Even like you could do this with over-the-counter supplements to see if they really are giving you as much vitamin C as they say they are. Oxidizing agents can be treated with excess iodide to produce triiodide, and the iodometric analysis is completed by titrating liberated triiodide with standard thiosulfate. And then again, because we're titrating with the triiodide, we don't want to form the starch iodine complex too early. And so we add it right before the endpoint, which we should hopefully have already determined as in a rough ballpark figure before we start. And then we can add this to get the color change when we need it. So here are some titrations with standard triiodide solutions. So these are iodometric titrations. So we're titrating with the triiodide. So for example, we can do tin, we can do arsenic, we can do things like sulfur dioxide, hydrogen sulfide, zinc, cadmium, hydrogen cyanide, cyanic acid, glucose, ascorbic acid, phosphoric acid. So glucose and other reducing sugars. This is a good way of determining sugars, good way of determining ascorbic acid. So it's really useful in those. And then we have iodometric titration. So this is titration of the triiodide. So we can analyze indirectly things like chloride, perchloric acid, or hypochloric acid. And we have here oxygen, we have iodide anions, peroxides, we have manganetes, manganese oxides, manganese oxide. We can even determine things like dichromate and cerium 4+.